This conference will now be recorded.
Thanks for joining us, everybody, for the Satellite Book Club Seminar Series, Session 21. I'm Jordan Girth with the National Weather Service Office of Observations. I hope you're staying well. Today, we're going to have a great presentation from Joe Senkowitz, the Chief of the Ocean Prediction Center Ocean Applications Branch, titled GOES SST Capabilities and AWIPS to Visualize Ocean Features. Before I introduce him, I'd just like to go through a few reminders. First, that this session is being recorded, so your colleagues who might be working shifts can review it later. We will have opportunity for Q&A after the presentation, so please put your questions into the chat room and we will use that to prioritize answering them. This week, we're fortunate to have Greg Mant, the Science and Operations Officer at the Weather Forecast Office in Detroit, to lead us through that post-presentation discussion. If you're interested in being a future presenter, please reach out to us. We'd love to have you, specifically if you're interested in talking about applications of satellite data from the field perspective. If you're looking for training, we have a great training team that can help with that, led by Brian Mata of the Office of the Chief Learning Officer. Please reach out to him if you have any difficulty locating training materials related to satellite data or otherwise. I'd like to thank the Tower S team, David Blutis and Lee Byerly, for their assistance in establishing this forum, as well as the Office of the Chief Learning Officer and the GOES-R and JPSS programs. Without further ado, I'd like to introduce Joe Senkowitz, who has spent over 30 years with NOAA focusing on marine weather over the mid and high latitudes of the North Pacific and North Atlantic. He has been a forecaster, senior forecaster, SUE, and branch chief within the Ocean Prediction Center, and has worked to exploit satellite remotely sense wind and waves and geostationary and polar imagery to enhance situational awareness. He trained as a professional mariner at SUNY Maritime College and served as mate and relief captain on tugboats based in New York Harbor before attending grad school at the University of Washington. So Joe, welcome to the Satellite Book Club today.
Thanks, Jordan, and thanks for the nice introduction. So I'm hoping that this is going to be a little bit of a sort of a fun seminar and or just a sort of a fun 30 minutes, basically, to kind of give you maybe a little bit of a different perspective when you're using imagery from the geostationary series that we have now, GOES-R, that there are capabilities where you may be focusing on one thing, and if you're in a coastal forecast office or in a lakes forecast office, but occasionally nature will allow you to see the underlying surface, not only terrestrial, but the ocean. And the ocean has an enormous amount of detail on the ocean surface, thermal detail, that we can now see when we don't have clouds covering masking the underlying surface. So this is a AWIPS screenshot from GOES east of the Gulf of Mexico from late last week on the 1st. And you can see the black are clouds, and we'll talk about how to do this. And the lighter gray shades, warmer are white and black is cold. And so, or cooler. And you can see that, yeah, there's an enormous amount of detail in the Gulf of Mexico. Cold front is pushed south, clear air along the coast from Texas, actually Brownsville, all the way over to the Big Bend area of Florida. And along the shelf, you can really see quite a bit of detail of the ocean. This is a static image. Fortunately, we have 5- and 10-minute image, full disk or CONUS from the series of satellites, and really we can actually see quite a few things. My purpose here is really to just give you a tease and let you investigate, in the future with your AWIPS. Let's see. There we go. Okay. So, but why is this important? Why? Whoops. Don't want to go too far ahead. Okay. So why sea surface temperature gradients? Okay, they are significant for weather, for marine weather, for a variety of different reasons. One of them is the manifestation of boundary layer static stability. It is either stable or a mixed, depending on what the temperature structure is. Do you have a very shallow inversion above the surface where the surface decouples? In other words, do you have cool air over warmer water where it's unstable? Or do you have warm air over cool water where you actually have a very stable, shallow inversion that actually decouples the free boundary layer from the ocean surface. And I'll give an example of that next. Also in cloud production, that we can see basically how the boundary layer manifests itself in shallow clouds being produced, or surface-based clouds being, for instance, when we have cold air advection and we have warmer water underneath, you actually will see the clouds will be produced in that area. Also, fog production and all are linked to underlying cool spots over the ocean, and the flow is how it sets up. The other one is that ocean current and our boundaries, and waves and wind can be significantly different over a warm ocean current that is flowing, for instance, in the Gulf Stream. And I will give an example of that, where the delineation of the Gulf Stream actually does have impacts on vessels that are transiting the stream. Okay, so here is the case. This is QuickScat way back when. It's still valid. We still see examples like this. The purple lines basically are where there are gradients of the underlying ocean surface. So this here is the Gulf Stream, the northern edge or north wall of the Gulf Stream, and this is a warm eddy up to the northwest of the main body of the Gulf Stream. The yellow are gale force winds, so minimal gale force, 35 to say 41 knots of wind over the warmer Gulf Stream waters. When you get north of the Gulf Stream, and this is a full latitude trough with southerly flow moving offshore, the pressure gradient's the same as you move northward. So the winds in a free atmosphere, without an underlying, say, an isothermal underlying ocean surface, the winds would be the same all the way across this image from south to north. But instead, we see, as you go from warm water to cooler water, that the wind speeds, as detected by measuring the roughness on the ocean surface, there's less roughness. Okay, so the wind speed drops basically significantly. So you're going from 35 knots, 30 knots, in some cases down to 15 knots. The roughness drops that significantly. It's a shallow inversion, but it's not making the same amount of roughness that is being made where the water is warmer. So warmer to cool, we see a drop in wind speed. We see this quite frequently in the spring off the east coast of the United States, and it happens on different scales. This is a warm eddy to the northwest on the upper left of the picture, where there's 30 knots of wind surrounded by a field of 15 to 20. That's a pool of circulating warm water compared to the cooler waters surrounding it. So that's an impact. And our numerical models used to really not have this factored in at all. That's quite different now with improved boundary layer schemes, especially on in the mesoscale models. Okay, so here's another example, sort of maybe a different way of looking at it. The green line in the image is the north wall of the Gulf Stream, and the yellow line is the south wall. This is that tanker, that's an oil tanker, heading south from Nova Scotia, and is slowing. That's what the color code means. So basically, the 12 knots green is 12 knots or greater, 6 to 11 knots is yellow, 2 to 6 knots of motion is orange or amber, and then red is less than 2 knots. So the ship is slow to begin with because there's weather, moving 6 to 11 knots, but then decreases speed significantly going through the stream. And you can see how the current effect on the ship as it avects eastward, moving slowly, because the underlying ocean is moving. And then when it basically gets out of the current, it's back moving again. So there's an impact to the vessel as it's going across the stream. This is not a insignificant thing for a ship that typically moves more than about 15 knots is at about 2 knots going through the stream. And the understanding is that it's basically the character of the waves is causing this ship to slow. It's not the only ship that we observed during a certain time period. So here's a graphic that will, this is the Gulf Stream. And during, from December of 2018 through the early April of 2019, we looked at the impacts of ships crossing the stream. And we have this data, it's called AIS data. and we've been able to sort of exploit it to kind of better understand the impacts of weather. And so I'm going to show a graphic that shows where ships were, where over this whole volume, as to where their typical reduction in speed was between 60 and 70% of normal. So for a 15-knot ship, that means that it was moving somewhere between 6 and 4.5 knots. That's impactful. That's less than half speed, obviously. So that's basically where we observed ships slowing significantly when they were passing through the Gulf Stream. So it marries up very well with the stream and even with the Gulf Stream farther out. So another significance of a ocean feature having an impact on weather. Okay, so now the fun part. So in AWIPS and with the ABI on GOES-R, 2 kilometer versus what we had for years, 4 kilometer IR. This is channel 13, 10.33 micron. We now have 5-minute imagery for CONUS. So the nearshore waters, the Great Lakes and all, West Coast are all certainly in that envelope. We have 10-minute imagery full disk. So we can look a variety of different places. The image on the right, that is Brazil and then Uruguay. And the delta, the La Plata River delta is there in the lower left-hand side. And that is one of the current systems off the South American coast, part of the South Atlantic Gyre. So typical imagery, we're all geared to looking at clouds. But this capability, you can exploit this by just playing with the color map and changing the color map. The example here is, it's part of the standard package. It is SAT, it is the visible, and it is linear. And then you have to play with the range and set the range for a max SST and a min SST. So you can actually kind of enhance on an area that you want and sort of favor it that way. The other part of looking at the underlying ocean is throttle the looping. Loop it as fast as your AWIPS will allow. And what will happen is you'll actually start to see the ocean start to stand out. Your eye will really be attracted to the ocean features, and you'll actually start to see that if you have a long enough loop, that you'll actually see the features in motion. And I'm going to show a couple of examples of this now. So let's start Gulf Stream. I've already mentioned it, and this is off the obviously the North Carolina coast. You can see the main body of the stream. It's not as clean a boundary as one would like. There are all kinds of filaments that come off the stream. Remember, it's a high shear zone, so it's not surprising that we see filaments come off, say south of Cape Fear, south of Cape Lookout. In here, there's another down to the south. This is known as a Charleston bump in here, where the stream typically takes a little bit of a jog to the east and then turns back to the north before its northeast progression. But I want to focus from Cape Hatteras southward, these darker blobs of cooler water. And I'll show you in a loop what those are. It caught my interest, and you can actually time these. And you look at there's gaps. So there's one here off of Ocracoke Inlet, and then there's another one that's just coming off, and the temperature sort of matches the temperature of the water in Pamlico and Albemarle Sound. I think what you're seeing is basically the ebb flow tide of water coming off out of the Sound, the cooler water coming out into the Atlantic. And you're seeing it from both Hatteras Inlet here and then Ocracoke Inlet there. And there are all kinds of marvelous features. If you look farther into the northeast of Hatteras, you see a beautiful axis of dilatation, deformation with a water that basically has come off the stream flowing westward and then actually diverging on the surface. So let's go ahead and take a look at this. And Bill Line put this together for me. So this is an example as the clouds clear out. It's a little gravelly because we're pushing the limits, but you can see these pulses of cooler water coming out of the sounds. I've seen examples with the Mississippi River where in the springtime, when there's a significant difference between the Mississippi River water temperature and the Gulf, that you'll see the plume extend quite a ways out from the stream. And in this case, you can see where those pulses actually, I mean, eventually they mix out, but they actually have some memory as they move out to the east and approach the northwest wall of the Gulf Stream. Okay, so here's a longer loop, and I regret showing an East Coast bias, perhaps, but this is where the clouds were free. But here, if you watch, just let your eyes sort of just graze over the ocean features, and you will see that pretty much every feature you see is in motion. You'll see sort of rotary motions. You will see, for instance, let's start up on the Gulf of Maine. You will see a pulsing over time, and you can see basically, assuming that that's the tidal action, basically in part manifesting itself. You can see sort of the difference between this sort of finger of cooler water from east of Cape Cod down to the southeast. You can certainly see the colder water up in the Gulf of Maine off the coast here where I am. If you look down and it just uncovers north of the Gulf Stream, you can see where there's Gulf Stream water, where there's very warm water, and that also has quite a bit of detail and gradients associated with it. Not a big, large eddy, but you can see that there are gradients. And also you can actually see, if you're even farther down east of North Carolina in the Outer Banks, you'll actually see the motion of the stream and the filaments as they're moving along up to the northeast. And even there's an eddy here to the north of the feature that we were talking about earlier. So let me go on to one more. And again, back to the Gulf of Mexico. Bill Line did these images for me, grabbed them. And even though there is, perhaps aerosols and some thin cloud, you can still see the features, even though they're relatively monochromatic in this enhancement. And I should say that this is a stock enhancement. It's IR, and I'm trying to remember, it's actually on one of the slides. You can go back and look and see what it is. But this enhancement at least allows you to sort of look on a gross scale and see the features. And if you want to look at something much finer, then go to the Viz linear and black and white, and that you can actually kind of hone in and really see some of the differences. And also you can use the sampling certainly with AWIPS. But here you can see the loop current is over here. As I take my cursor and then the clouds come over it. But this is a loop right in here. There are eddies right in here. There's an eddy right there, and you can see a lot of the structure in the stream in the Gulf that we typically think of sort of just a warm bathtub, but it has quite a bit of thermal structure in it. So I was going to try and go to AWIPS. I'm out of time, so I'm not going to do that. So ABI, we really have some phenomenal capabilities with ABI. I was dying for GOES-R to be launched so that we could start to play with the and start to see some of the ocean features. And the right-hand figure here basically is off of Uruguay and southern Brazil, and where you really get to see some of the thermal gradients and how very, very strong they are, and what the capabilities of the ABI has without even looping. But when you loop it, you get to see that everything's moving. The features evolve at different scales, but the ocean does move at the mesoscale or even the small mesoscale. And that's the point, is that it's not static, that it is changing. It's reacting obviously to wind forcing, to thermal heating. You can see where, there's a calm area, and it actually does, with the SST, it does heat during the day. There's a diurnal signal, and you can even see the pulses that I showed. But the important thing is that the ocean's not static. Even a day-long image really doesn't give credit to the structure of the ocean. So with ABI, with GOES-R series, we can view the ocean in motion, and I encourage you to give it a try. Thank you.
Thanks, Joe. This is Greg Mann, WFO Detroit. Couple comments. Obviously, in the Great Lakes, we've leveraged some of this information as well. Upwelling events are a pretty big deal during parts of the time of the year, especially when we got a lot of warm surface water and then a strong offshore flow. So we certainly see a lot of upwelling. I guess a question to you from the atmospheric science side of things is, do you think that you could be able to surmise maybe where there's now granted you have scatterometer data to help out as well, but where there's enough strong clear airflow that you would start to see enhanced mixing going on in the water surface to help delineate whether or not you can surmise that flow is getting to the surface? It's back to how well are things mixing, and would a surface water temperature change be dramatic enough to show up in a relatively short time scale to kind of gain confidence that there's stronger flow out there?
I think if you look routinely, like say make it a daily thing to check and see. In fact, I was looking at Lake Michigan 2 days ago, and you could see that it looked like there had been upwelling with westerly flow along the western shore and extending out quite a ways. With this capability, if we make it a routine to look at the lake, the lakes, the ocean, we will start to see the subtle responses. Now, it has to be cloud free, and offshore flow, typically, at least for this time of year, you won't see the cumulus forming right along the coast. They'll be offshore. So I think if we can learn over time as to how to better, what are the responses, and then how do we apply those responses in our daily routine in our products.
All right, excellent. We did have one question from Scott Lidstrom. His question was, how is the south wall of the Gulf Stream defined? He doesn't recall a clear south edge in satellite compared to, say, the north wall.
So actually, that's a good question. I'm trying to remember. I know the north wall has several different definitions. I mean, there's a surface-based one, there's a depth-based one. I'm trying to remember what the depth is, what isotherm it is. But I'm gonna actually go back and see. I don't have it there, and I actually don't. Well, so we use a Navy analysis where they're really focused on trying to have an understanding as to where the current maximum is, and they're typically looking at the weaker thermal gradient on the south side of the Gulf Stream. I think it's not as well. Well, one thing is naturally it's not as well defined, but also I actually don't know what the definition is that they're using for that. But I know, for instance, my guess is that if back in this image, they're probably indicating where the really warm water is to the gradient and putting the sort of like the way we do fronts is basically putting the boundary on where on one side of the gradient, basically on the warm side of the gradient.
Have you noticed in kind of going back to the cloud side of things, since we are getting into the unstable season, and we'll obviously see cloud formation pretty quickly off of the coast. Have you noticed where maybe prior to, say, a frontal approach where you have a good clear sky view, and then in a post-frontal environment, if there's still like correlation with those hot spots in the new cloud formation? Because obviously in the ocean, on the downstream side, there's it's the shipping lanes that might be impacted by certain things. Obviously on the Great Lakes, the downstream side, wherever the bands themselves set up first, they become the dominant vertical circulation processes that then highlight where the dominant precipitation band might be downstream. And of course that does happen certainly in certain cases on the ocean as well. Do you see maybe that there's some correlation if you did enough upfront work looking at where the warm pockets were, that you can maybe get a heads up on maybe where the preferential development might occur?
So yes, and I put this Gulf of Mexico image back up. So I pointed out there's a portion of the loop current right here, sort of south of Pensacola area. And if you watch over time, the clouds form just downstream of that warm area. So as the front is pushed southward, basically there are RQ, and then the cumulus basically start to form to the south of Pensacola down to the southwest. and you can trace that back to a warm spot. And I've seen that on the Atlantic, certainly in the Atlantic side where there's a tongue of warm water, and you will see if streamers of Q, cloud streets actually start to form, not necessarily on that boundary, but just downwind of that boundary. So yeah, so let me answer it that way.
All right, that's very helpful. We are coming close to 28 after. I'm not seeing any other audience questions at this time. We'll kind of hold on for a minute or two to see if we get any other questions. In your last couple of minutes, is there anything else that you wanna? I guess I'd ask the question: Are some of these either through a job sheet perspective or techniques, or is there thoughts of building custom color curves outside of what the stock color curves are that could get posted to, say, VLab for people to extract and use?
Actually, that's a good point, and I think that would be the next step. I know Bill basically suggested how to use an existing IR enhancement. I have it right there. Okay, so GOES-R IR enhanced rainbow warmer yellow, but then the trick is to reverse the temperature basically. So the max is 0, and then the min.
Right. You flip the color curve.
You're just flipping the color curve. So it actually goes, so it goes from warm is actually warm colors and cool is cool colors. And that's the example that's underneath. And you can play with that to sort of enhance for your own area. It doesn't have to be 30 degrees C temperature range, but this, kind of gives you the broad view of where the features are and how they're evolving.
All right, excellent. Well, obviously to the audience, if you come up with a nifty way of taking advantage of all this bit depth that we have with the series of GOES information, that a color curve that can take advantage of that and maybe filter other things just so they don't catch your eye, that obviously be really helpful, I think, for everyone. Because a lot of this is like, we know the information's there, and most of it's just trying to visualize it in a way that it's implicit to the eye so that you can get to that higher level interpretation.
And that's why I always started with the gray shade, because that way, I mean, it wasn't a mask, but at least the clouds were black. So, and if you just let it run, especially if you can run it quickly, let it loop quickly, then you actually really your eye is attracted to where there's motion and where there are features.
All right, excellent. Well, I guess I pass the baton back to Jordan, and he can close up shop then.
Thanks so much, Greg, for leading that discussion, and thanks, Joe, for your presentation. That was great. Always learn something, and use of sea surface temperature data is sometimes overlooked, but can be very informative. So thank you so much for your presentation today. If you have questions, or I should say that you didn't get to answer, please feel free to reach out to Joe or get in touch with us, and we can put you in touch. There is a survey in the chat you'll see related to the Satellite Book Club. We want to make sure this is meeting your needs. Feel free to fill that out. I hope you're planning on joining us next week, Thursday, October 15th. Once again at 12 noon Eastern time, we have Jason Jordan, who's a master instructor at the Forecast Decision Training Division in Boulder, and he's going to be presenting on the intricacies of GLM data and some of the applications that he discovered while working in operations. So look for an email on that from the Tower S team. Just a reminder, if you need help installing the latest Tower S RPM or your ITO does, please get in touch with John Evans and Lee Byerly. They are standing by and ready to assist you. So please remember to update to your latest RPM at your field office when you have the opportunity. With that, thanks for joining us. I hope you have a good weekend whenever that comes for you. Stay well, and we'll see you next week. Take care.